Welcome back to our quest to understand the mechanism behind star lifetimes, fusion, fission, and much more. Last time, we did the hard work of figuring out what binding energy is. We looked at the puzzle of the mass defect, figured out how to use Einstein's mass energy equivalence, and calculated a binding energy. There's one glaring issue though. We only know it for deuterium. Next up in our journey, we're going to figure out how to take this concept and generalize it to any atom, regardless of how many nucleons it has. Before we get going, we need to make sure we understand the difference between an analytical solution to a problem and a numerical solution to that same problem. Put simply, an analytical solution is one where the answer is exact, while a numerical solution is an estimation. Let's bring back Joe, our proton, and Bob, our neutron. We'll take a look at a couple examples and then get a little bit more detailed. Let's say, for example, that we had 100 Joes and 100 Bobs, and we wanted to know what the mass of them all added up was prior to them getting put together into nuclei. Not too hard to solve, right? We multiply Joe's mass by 100, add 100 of Bob's mass to that, and we have our answer. Let's take a second and write this out as an equation. To do that, let's give Joe and Bob's mass their own symbols. We'll go with J for Joe and B for Bob. Now, we can say the total mass is equivalent to 100 of J and 100 of B, or in other words, 100 J and 100 B. This right here is an analytical solution to our problem. It's an exact solution with no room for error. We didn't estimate anything, and the formula works out to an exact solution no matter what we plug in for B and J. On the other hand, let's look at a numerical approach to a very similar problem. Let's say for now that Bob has a mass of 1 unit and Joe has a mass of 2 units. It doesn't really matter what unit. If I have a total of 100 units of mass, and I counted up that I have 50 Bobs, how many Joes do I have? Let's set up an equation for this. We have 50 Bobs, so 50B, and we have some number of Joes which we don't know. Exactly the same as before, we can refer to this unknown number with a symbol. In this case, I'll use X to represent it. We have X Joes, so we'll write this as XJ. Let's add the two together, 50B plus XJ. We know this has to be equivalent to a total of 100, so 50B plus XJ equals 100. This equation isn't particularly complex, and we could quickly solve for X analytically, but let's try it numerically. What we'll do is guess a number for X, evaluate it, and then adjust our guess from there. Let's start by guessing there's 10 Joes, so X equals 10. 50 Bobs weigh 50 units in our problem, and 10 Joes weigh 2 times 10, so 20 units, which means put together they add up to 70 units. This guess put us lower than 100, which is what we wanted, so there must be more than 10 Joes. Let's make a second guess, but this time we'll pick a bigger number. How about 30? Our equation this time will be 50B plus 30J equals 100. 50 Bobs still weigh 50 units, and this time 30 Joes weigh 60 units, so added up we get a total of 110 units. We've overestimated a little this time, so now we know our answer must be between 10 and 30 somewhere. After making enough guesses, we'd find that there are 50 Bobs and 25 Joes. 50 plus 50 equals 100. This kind of smart guess and check is similar to what's called the bisection method in numerical analysis, where we narrow down the answer by repeatedly cutting the range of possible answers in half. So, why did that matter? The question we want to solve, what is the binding energy of any atom, relies on us having some sort of formula to solve. We want to say, I have this many protons and this many neutrons in my nucleus. What's the total mass of it? In other words, we're looking for some formula that can take the values we have for our protons and neutrons and then spit out our answer. At this point, we'll have to discuss one unsatisfying element of our exploration. This section will be less rigorous than our other deep dives because there is no analytical formula for finding the mass defect of any atom. Instead, we'll take a more surface level approach. Together, we'll explore the Bethe-Weiszäcker semi-empirical mass formula. Before we hop into that, let's first get a quick definition. What is a semi-empirical formula in the first place? We call this formula semi-empirical because it combines the theoretical formula with experimental values that we measure. More on that in a second, but for now, let's take a look at this formula. Yikes. There's a ton of stuff going on here, but we can simplify this down to something a bit less awful to look at. First up, let's understand what each piece of this does, looking at just the upper section first. M tot is the mass of our nucleus. In other words, it's the answer to the question we have. The rest of the formula will tell us how we get there. The n and z in our equation do the same thing as the x we used in the numerical analysis we did earlier. They just represent an amount of our neutrons and protons, respectively. You'll notice that the n is tied to an m sub n, and the z and m sub p. These represent the mass of a single neutron and the mass of a single proton, respectively. This part of our puzzle says if I have n neutrons, then the total mass of them is n times m sub n, and if I have z protons, then the total mass of them is z times m sub p. This chunk of our equation, nmn plus zmp, is what we did in our analytical solution earlier. Instead of the m's, we had b and j, and the n and z were both equal to 100. This time we've used variables to represent the amount of each particle we have, so we can change it from 100 to whatever we want. Now we've come to the ugliest term of the bunch, this E sub b over c squared term. The E sub b term is what we need to pay attention to. That is our binding energy. Let's take a quick look at how that's calculated using this formula. This looks scary, but what I want us to see is that there's a bunch of n's and z's along with these four a something terms. The n's and z's here are the exact same thing as earlier. They just represent the number of protons and neutrons in our nucleus. Those capital A's reference the total nucleon number for the atom. They're just n and z added up. Those a something terms are coefficients that we tuned to fit real life. We measured the mass of real nuclei and then adjusted the four a something terms in our equation to make our formula match what we saw in reality, thus the label semi-empirical. This is similar to our numerical approach. We kind of guess at what values we should tune each coefficient to and then adjust our guess to fit real data. Critically, this isn't a prediction of real life, but rather a model of it. What we want to do with this formula is find a way to simplify it down to something that we can easily calculate things with. Remember earlier when we wrote that E was equivalent to delta mc squared? Let's just ignore the full-sized binding energy formula for a second and plug delta mc squared in place of the E sub b term. Now we have delta mc squared divided by c squared, which lets us cancel that term and simplify. We're left with m total equals n times m sub n plus z times m sub p minus delta m. Delta m is a term we've seen before too. It's the mass defect from earlier. Take a look at this addition at the start. This is telling us to add up all the masses of the neutrons and protons. Our simplification, just like earlier, seems to be telling us that to get the mass of a nucleus, we should multiply the number of protons by its mass, add that to the number of neutrons multiplied by its mass, and then subtract the mass defect. The same exact process we used for the deuterium atom from earlier. In fact, in our original case, we used exactly this formula. Our n and z were just both equivalent to 1. How do we know this is right though? What's a way we could see if we're on the right track? Let's test this out. If this formula really works, it should let us predict the mass defect and binding energy of any atom we choose. Let's see how it holds up. In order to calculate our mass defect, we'll follow the same path we used for deuterium. We'll measure the mass of an atom's nucleus and compare it to how massive its individual pieces are. Importantly, we're not calculating the mass of the nucleus, we're measuring it. For an actual calculation using the semi-empirical mass formula, keep an eye out for my office hours on this topic where I'll delve deeper into the use of it. For now, we'll go ahead and rearrange our formula a little bit. We're going to weigh our atom, so we know M total from the beginning. What we don't know is delta M, the mass defect. The M sub n and M sub p added together give us the expected mass of the nucleus, so if we subtract the measured mass from that like earlier, we'll get our mass defect. Let's give this a shot for helium. Helium's nucleus has 2 protons and 2 neutrons in its stable isotope, so N and Z will both be equal to 2. The mass of a neutron is roughly 1.675 times 10 to the negative 27th kilos, and the mass of a proton is roughly 1.673 times 10 to the negative 27th kilos. We'll multiply both of those by 2 and then add them together. Our expected mass is 6.696 times 10 to the negative 27th kilos. To find our measured mass, we'll do the same thing as the start, and we'll weigh a bunch of helium nuclei, then divide the total mass of those nuclei by the number of them, thus giving us a measured mass of 6.646 times 10 to the negative 27th kilograms. Now we just find the difference between the two and we have our mass defect. Lastly, all we need to do is take this number and plug it back into Einstein's formula from last episode. Plug in our mass defect for delta M, convert our kilogram meters squared per second squared into joules, and there it is. We just calculated that the binding energy of helium is 5.0 times 10 to the negative 12th joules, or roughly 28.1 mega electron volts. Now we can take our formula from the start and generalize it to any atom of any size nucleus. We've done a ton of work coming up with a formula that we can apply to get the binding energy of whatever nucleus we want. Now we can move on to the interesting part, comparing them. I'll put on screen the first 5 atoms on the periodic table's binding energies. Do you see a trend? As the atom gets bigger, the number goes up, and it grows really fast. This isn't super helpful to us in its current state since it really doesn't tell us all that much. Of course the number goes up when there's more stuff involved. Let's try something a little different. Let's take each of these nuclei and list the number of nucleons in them. How many protons and neutrons are there in each? Next, we can do the very same trick we used when we found the measured masses of the nuclei. We'll divide the total binding energy of the whole nucleus by the number of pieces that comprise it, thus giving us the binding energy per nucleon of each atom. We can compare this much more easily between atoms. This gives us a bunch of information, namely what we care about is how big this number is. That tells us how tightly the protons and neutrons are held within our nucleus. A big number means our protons and neutrons are held tightly together. They're bound with a lot of energy. A small number means they're loosely held. We can break them apart with less effort. And with that, we can move on to our final step, constructing the binding energy curve. Time for all of our pieces of the puzzle to come together. We're going to start by creating a graph. The x-axis will be our list of elements. I'm going to label them 1 for hydrogen, 2 for helium, 3 for lithium, and so on. The y-axis will be our binding energies per nucleon. Low values will be near 0, high values will go up. We'll span this from 0 to 10 mega electron volts per nucleon. What we'll do now is take each of the values we calculated earlier for those first 5 elements and put them on our graph. We see something kind of neat. The binding energy shoots up quickly from 0 to around 7.5 mega electron volts per nucleon, drops back down, and then climbs again. Let's expand this out to 10 elements and see what happens. An important caveat as we do this, I'm going to use data on the most naturally abundant, stable isotope of each of these elements as we go on here. The number of neutrons and protons is not equal for many of the larger elements, and there's many isotopes. We'll discuss this more in detail in future videos. Okay, at this range, there's definitely some sort of upward trend. The binding energy per nucleon has gone up again, now getting all the way up to 8.11 mega electron volts per nucleon for sodium. Clearly, there's some trend here. Let's go up now to 25 elements. Now there seems to be a different thing happening. As the atoms get bigger, it looks like our binding energy per nucleon is starting to level off at just under 9 mega electron volts per nucleon. Let's take this one more step up and go all the way through the first 50 elements. One more caveat though. Technetium, the 43rd element, has no stable isotope, so I used an average of several of its more abundant forms. Notice something interesting here? Our binding energy per nucleon went up, but only till we got here, to iron. After this, we get another similarly high peak at nickel, and then everything else starts to drop back down. This right here gives us the answer to the question I asked at the beginning of this series, the question on the practice exam. Out of the choices we had, the element with the highest binding energy per nucleon is iron, with a binding energy of 8.79 mega electron volts per nucleon. After our journey from the early 1900s to today, from the humble proton and electron to every element, we've learned a lot. We figured out what the binding energy of an atom is by using Einstein's famous mass-energy equivalence on the mass defect of deuterium. Next, we generalized that to any atom by taking a look at the Bethe-Weiszäcker formula, and then simplifying it to something we could use to compare atoms. After this, we figured out how to compare that between atoms by dividing the binding energy by the number of nucleons in each atom. Finally, we even graphed it, allowing us to see for sure that iron indeed has the highest binding energy per nucleon. Now, I know I didn't tell you why the graph looks the way it is and only really talked about what it looked like. This graph is much more far-reaching than just the stuff we've talked about so far. In fact, not only can we answer why stars die with it, we can even explain things like why uranium reactors work and why the universe has the amounts of each element that it has. Catch the next part for all that, where we'll chat about my favorite part of all this, why it matters and why you should care about it.